Welcome back to ECE 320A. In this video, what I want to do is apply these Laplace transform strategies, inverse Laplace transform, to analyze a first-order circuit to show how you can connect these these mathematical tools into a physical system problem. And again, we're in Unit 5. At the end of this unit, you'll have exam number 2, and you can look at some supplemental videos dealing with inverse Laplace transforms and using the power of your calculator, either the TI-89 or the Inspire. You should be able to follow along and use those same strategies with the TI Inspire. They may be modified just slightly. But let's look at circuit analysis in the S domain, and I think by this point in your academic career, you probably recognize this particular circuit as a low-pass filter. It's first order. We have one energy storage device, so when we're doing these equations, we should expect a first-order differential equation, or now that we're doing frequency domain analysis, we should be expecting a first-order denominator expression that's consistent with the order of the differential equation or system that we have that we're working with. What we want to do now is find the governing dynamics of this system, and let's go ahead now as a starting process. We'll do this differently in a subsequent set of videos, but now let's go ahead and try to write these equations, the governing dynamics, in the time domain, and then move into the frequency domain. Subsequent to this, we'll work immediately in the S domain, and we'll find an S domain equivalent circuit and push that analysis through in the S domain, and at the very end come back into the time domain. Let's now look at a strategy that develops time domain differential equations and then convert those into the S domain, and then once we have our expression in the S domain, inverse Laplace to find the actual value. And in this case, we want to find what's the output voltage across that capacitor in this low-pass filter. And based on Eli and ICE, typically when you want to be writing differential equations, what you focus on are these last variables. We have a capacitor, there's no inductor, so now we're dealing with the ICE. We want to now probably in our strategy focus on E, or the voltage, or write our differential equations in terms of the capacitor voltage, and that will usually allow us a cleaner way of coming up with the differential equations. Now, anticipating using ICE, ICE deals with finding a current expression. Let's go ahead and now write a Kcl equation at node A, and we could say, let's just worry about the sum of currents, algebraic sum, and in this case, if I define my resistor current to go out of the node, now I just have to sum those currents, and the sum of those currents equals 0. There's no current going to the open terminal to the right. I just have two currents exiting node A. So now if I perform my Kcl at that node, I should say, or be able to confidently state that the resistor current plus the capacitor current must sum to 0, since the sum of those currents exiting that node have to equal 0. Now, what is the capacitor current? Well, ICE gives us that, I sub C of t. Now again, we wanted to write this in terms of capacitor voltage, and ICE tells us then that that will give us the capacitor voltage that we want. ICE says I is equal to C, V sub C prime of t, or C dV dt. Now we have an expression for the capacitor's current in terms of the capacitor's voltage, and I sub R of t, just using Ohm's law, we have the voltage dropped across that resistor. We don't really need to worry about how I've labeled V sub R. The voltage dropped when we want I sub R to be moving to the left in a to be positive, then we would consider node A to be at the more positive polarity, even though it's not. But we would just say V sub C of t, that's the voltage at A, minus V of t, divided by R gives us a positive current I sub R going from right to left. Or we now have that V sub C of t minus V of t, is that what I called my source voltage, divided by R is I sub R of t. I can now use those two relationships for I sub C and I sub R to find one equation that does indeed hold for that circuit, and it's written in terms of capacitor voltages and their derivatives and the source voltage. Here I have V sub C of t minus V of t over R is my resistor current. If I multiply, or I should say, let me isolate on V sub C prime, or make its coefficient 1, or create a monic, what will eventually be a monic polynomial in S. Let me divide both sides by C, or all terms by C, and I now can say that I have this differential equation V sub C prime of t plus 1 over RC V sub C of t equaling 1 over RC V of t. Putting the source terms on the right and the dependent terms, or the capacitor voltage terms, on the left. That's now the governing differential equation. We should be feeling a little bit more comfortable. It's first order. We have a first derivative. We now need to solve that for various source voltage expressions V of t. So let's go ahead now and do this solution of a differential equation by using the Laplace transform techniques, which means that now let's Laplace transform this time domain equation, get into the frequency domain. We'll move into the frequency domain. We'll do our manipulation. We'll try to now find terms, or the structures that we want in the frequency domain, and we can immediately then, using the transform tables, pull those back into the time domain to find the time domain waveform for our voltage, V sub C of t, that satisfies that governing differential equation. Let's now take into the frequency domain. Or maybe I'll say let's move into the S domain, same difference, by Laplace transforming the differential equation. If we do it, we know the Laplace transform is a linear operation, so we can Laplace transform each of those three terms separately or independently. We have the Laplace transform of the derivative of our capacitor voltage plus a weighted Laplace transform of the capacitor voltage equaling a weighted Laplace transform of our source voltage V of t. We then have the Laplace transform of V sub C prime of t plus 1 over RC Laplace transform of V sub C of t equaling 1 over RC, the Laplace transform of our source. Let's now apply some of the Laplace transform properties that we know. We now know the Laplace transform of a derivative will be s times the Laplace transform of the waveform, which is now capital V sub c of t, minus the initial condition in the time domain on that capacitor voltage at time 0 minus. Again, we're dealing with non-negative arguments of time, or one-sided Laplace transforms, plus 1 over RC V sub c of s equaling 1 over RC, and we don't know yet what we've decided to use for the applied voltage waveform, little v of t, so let's just say we'll work with that and assume that we now know its Laplace transform, capital V of s, when needed. To solve this, we want to solve this in terms of the unknown that we're after, which is the capacitor's voltage, meaning let's now isolate or combine all of the terms that are associated with capital V sub c of s. Doing that, we now have s times V sub c of s plus 1 over RC V sub c of s. And we can now put the initial condition term on the right-hand side along with our forcing term. We have 1 over RC V of s plus V sub c of 0 minus. Or we now have s plus 1 over RC, scaling or a polynomial weighting our capacitor's Laplace transform V sub c of s, and that's 1 over RC capital V of s plus V sub c of 0 minus. V sub c of 0 minus is the initial condition on our capacitor voltage, and this polynomial that's weighting our unknown that we're trying to solve for, which is the capacitor voltage, this now gives us our system's characteristic behavior, and we then call this the characteristic polynomial, because the values of s that cause that polynomial to vanish provide us with the frequencies associated with, or the complex values of s that we naturally will see appearing from this particular system. And in this case, it's going to be a real value of s that makes that polynomial vanish or equal 0, which now says that if we have a real value of s for a root of our characteristic polynomial, that will now give us an exponentially decaying weight on all of the other terms, or that will now provide our transient behavior in the time domain response. Let's now solve for capital V sub c of s by dividing all sides by that characteristic polynomial. We then have 1 over RC, that's just a constant, divided by s plus 1 over RC. That scales our forcing function, or the applied voltage's Laplace transform, capital V of s, plus our initial condition divided by that same characteristic polynomial, s plus 1 over RC. This first piece is now our forced term in our response, and this second piece is a piece due to the initial condition in our system. Let's now look at some particular instances of an applied waveform, little v of t, and maybe some initial condition combinations. Suppose that somebody tells us that the initial condition on the capacitor at 0 minus was 2 volts, and they then apply for a forcing function a unit step. we want to know what's the capacitor voltage going to do in response to an initial condition of 2 and a unit step applied at time 0 to this particular circuit. Well, if we know that the generator or the voltage source is a unit step, we can immediately find capital V of S, its Laplace transform. That's now just 1 over S. So everywhere we had capital V of S, which is right here, we can now replace that with 1 over S. Or our V sub C of S expression is now 1 over RC. We haven't yet selected particular values for resistor and capacitor in our low-pass filter, and we aren't. We'll just keep it in terms of R and C, but now this is scaled by 1 over S, so that gives us an S, an additional S in the denominator. Then we had our initial condition, which we said was 2, divided by 1 over RC. Now we have two terms, but they're not quite yet in a partial fraction sense or form, so let's go ahead and do a partial fraction expansion. The second term looks fine, but the first term now is a second order, has a second order denominator, it has a constant numerator, it's strictly proper, so we can immediately start finding the partial fraction expansion of that first piece. In this case, V sub C of S is now some A over S plus some B over S plus 1 over RC plus 2 over S plus 1 over RC. Whatever 1 over RC is, that will give us our pole location, and the last of those three terms is already determined. It's now 2 in the time domain. The weighting would be 2, and its functional form would be e to the minus 1 over RC times time t. Or we now know the structure of the time domain voltage due to an initial condition of 2 volts and a step input. We now know that we will have A, U of t, once we've found A, plus B, e to the minus 1 over RC. That's the value of S that causes that denominator to vanish, t, plus 2 e to the minus 1 over RC times t. And this is true for t greater than or equal to 0. And in fact, if you go through the partial fraction expansion, I will go ahead and let you do that on your own, but if you did that for this particular piece, then you will find, in fact, that A becomes 1 and B becomes minus 1, irrespective of what RC is equal to. So that now V sub C of t actually becomes 1. That's 1 times the unit step, and we'll just say that we're only worrying about this for non-negative values of t. So A is 1, U of t is 1, B is minus 1. We now have minus e to the minus 1 over RC t plus 2 e to the minus 1 over RC t for t greater than or equal to 0. Or we now have a couple of terms that have the same exponential weighting or shape, waveform associated with them. We could combine those. V sub C of t now becomes 1 plus e to the minus 1 over RC t, and that's true for t greater than or equal to 0, and we can make that happen by simply switching it on with the unit step. Or if you don't like that way of writing it, just say 1 plus e to the minus 1 over RCT for t greater than or equal to 0. And what does that actually look like as a function of time? Again, we're trying to get some insight into this. For large values of time, where will v sub c of t live? If we examine v sub c of t for large values of time t, I hope that you see that that second term will eventually be gone. It will vanish. And so we actually will eventually end up approaching 1. At time t equals 0, where do we start? Well, the 1 is going to add on to whatever e to the minus 1 over RCt is, and at t equals 0, that's e to the 0 or 1. So we're actually starting up here at 1 plus 1 or 2, and then we want to eventually end up out here. And how do we end up there? Well, we exponentially decay down to there. And that's now what our time domain waveform will look like. Now, you might be saying, well, what's our time axis? Well, we can start to understand where we will be at what values from 2 to 1 by understanding this exponential. And the exponential is influenced by that value of s that solves s plus 1 over rc equal to 0, or it's influenced by this rc value. If we wanted to say, oh, well, what if that exponential was actually at 5 or minus 5? Or we're now saying that we have e to the minus 1 over rc, and what will make that exponent be equal to 5? Well, when 5 rc is what t is. So here we are actually saying, let's let t equal 5 rc. We're actually going to see that rc is our time constant tau. So now we're looking for what happens after 5 time constants. Well, if you compute on your calculator e to the minus 5, you will find that that becomes 0.0067, and that's, I hope you'll agree, small, but in fact, we typically say, well, we maybe can approximate this to be approximately 0.01 if we round. So e to the minus 5 is assumed to be within 1% of our final or 1% of where we started. We started at 2, we're going to 1, so we'll be within 1% of 1 after 5 time constants. And whatever 5 time constants is obviously hinges on this product of RC. But if we said, if we were drawing this, and I wished I would have done tick marks a little differently, but actually it's not too bad. We could sort of say there's tau, here's 2 tau, here's 3 tau, here's 4 tau, and here's 5 tau. So whatever tau is, which is RC, by that point in time, we will be 1% from our initial value towards our final value. And in this case, we're 1% away from 1 at 5 tau, or e to the minus 5. And you can actually see that if we looked at different values of these exponents, if we looked at e to the minus 1, that's 1 over e, and that will occur when t is equal to rc, or that's actually 1 time constant, and this is 0.367 in terms of a value. So at 1 time constant, my sketch is not very accurate, but we're 37% towards our final value. So this is now like a 37% of the distance between where we started and where we're going to end up. This is now 1 time constant. And that's when 1 over RC times tau is equal to 1, or when tau is equal to RC. So in this first order low-pass filter built from one resistor and one capacitor, the time constant, tau, is RC. And we can talk now in terms of time constants. One time constant into this evolution of the response, and we are 37% of the distance between 2 and 1 in reaching our destination, or our final value of 1. In two time constants, which would be e to the minus 2, that's when t is equal to 2rc. If you looked at this, this is now 1 over e squared, or ends up being 0.1353, or roughly 14%. Now we're getting pretty close, and that's not too far into this evolution of our system response. We're now 14% of the distance between our initial value and the final value. If we carry this even further, if we go to 3 time constants, that's now 1 over e cubed, and this now is a value of 0.04979. So this is approximately 5%. So we're now, after 3 time constants, we're within 5% of where we want to end up, or will end up. E to the minus 4 is actually 0.01832, and typically that gets approximated to be 2%. So now after 4 time constants, and sometimes that people will say, oh, 2% is our final value designation. That now happens in 4 time constants, and it's now 2% of the way from our initial value to the final value. And as we said before, our 1% settling time is influenced by 5 time constants, which in this RC circuit, first order is RC, and sometimes we'll denote that as T sub S. This is now our time constant, tau. That's now one particular combination of initial condition and forcing function. What happens if we were to look at a different combination? Suppose that we didn't have an initial condition on our capacitor. Suppose that we started the capacitor uncharged. It's now at 0 volts. And let's say that our applied voltage, V of t, is a cosine omega t u of t. So we turn on a cosine waveform at time t equals 0. So we hit this system, this low-pass filter, with a sinusoid, a pure sinusoid. It's not damped. It's just continuing to oscillate at a frequency of omega radians per second. Now we can say, oh, we know what the Laplace transform of little v of t is. That's now as over s squared plus omega squared. And with that v of s, we now know that v sub c of s, now we don't have to repeat much of the analysis. We now can use this starting expression, and the second term is no longer there because we have 0 initial conditions. We now simply need to scale capital V of s, or multiply it by the 1 over RC divided by s plus 1 over RC to obtain capital V sub c of s. Or V sub c of s is now 1 over RC over S plus 1 over RC times AS over S squared plus omega squared. And I hope now that you know, oh, I can now do a partial fraction expansion because my denominator is third order, my numerator is first order, it's strictly proper. I can immediately say that V sub C of S is going to have, and I have what? I have a complex root at plus and minus j omega. That means that I'm going to have a sinusoidal response in the steady state, a cosine and a sine probably, and I'm going to have a factor in my partial fraction expansion associated with the real denominator factor, s plus 1 over rc. So that I now could say that I have an a1 over s plus 1 over rc plus some amount of pure cosine, which I'll say is b1, scaling s over s squared plus omega squared, and some weighting on a sine, pure sine wave, which is now going to come in with a weighting of c sub 1. I now can immediately say that that's the structure of my Laplace transform capacitor's voltage. And that now allows me to immediately write down the structure of the time domain solution. I now know I have A1 e to the minus 1 over RC times t. That's an exponentially decaying. That will have a transient plus a B1 cosine omega t plus a C1 sine omega t. And all of that is going to happen after, or for non-negative values of time t, or after t equals 0. I now can compartmentalize this or break this down into a transient term due to the circuit itself, or the RC low-pass filter, and that transient depends on the time constant of that low-pass filter, RC, and I have a forced response because I was applying a cosine waveform with a frequency of omega. And the output frequency, the frequency in the sinusoidal steady state is equal to the input's frequency. If I'm shaking this system at a frequency of omega, thankfully the system just shakes at that frequency omega. There's no change in the frequency. I excite it at omega, and the system just eventually starts shaking at a frequency of omega. And how long do I have to wait before all I see is shaking and no more transient? Now I have to wait. Do I have to wait an infinite amount of time? Theoretically, yes. But in reality, this transient is negligible after, let's just agree, 5 time constants. When we get within 1% of where we're going, 5 tau, and in this low-pass filter, t of 5 tau is 5 RC. So after 5 RC in real time, all we will see are this second and third term in this sinusoidal steady state output, and they will be shaking or vibrating at a frequency omega, which is the same frequency as our input's frequency. That now allows you to see how you can utilize, starting with some original analysis, boiling it down to the expression for capital V sub C of S in the frequency domain. Now you can start plugging in all sorts of combinations for initial conditions and excitations to see what's going to happen to that capacitor's voltage in the time domain. We could hit it with an exponentially damped cosine. We could hit it with a ramp. We could have zero initial conditions. We could have non-zero initial conditions, all different kinds of combinations, but all of those could be starting with this particular expression. We wouldn't have to go back to square one. We've now done most of the analysis. Now the only remaining piece would be to plug in the appropriate input and initial condition for the different combinations that somebody might be requesting. That should give you a better feel for how to apply in real life, in a real life setting, these concepts of Laplace transforms and their inverses.